Hi, and welcome back to our Simultaneous Equations and Quadratics chapter. This is part 3, in which we'll look at what do we do when we have simultaneous equations with one linear, one nonlinear. And as a bonus, we're going to also talk about where does the equation for a circle come from and how does that work. Hopefully by the end of this lesson, you'll be able to say, I can solve simultaneous equations where one is nonlinear, including where one equation is a circle, and I can recognize that the equation of a circle is x squared plus y squared equals r squared. You may already know that, but we'll talk about that. All right, so we know that, what does that mean, nonlinear? It means it's not a straight line. It's an equation where the exponent of the variable is 2 or more. Something like y equals x squared plus 6. Here's a graph that's nonlinear. It's the graph of y equals x squared plus 2x minus 3. So if we were asked to solve where does this equal 0, we talked about this previously and last year that we'd look for the line where y equals 0. And that's the line that is actually the x-axis. Y is 0 all the way along there. And you're looking for where these lines cross. You can also see this by factorizing and seeing, well, where would we get these points if we said that this equation was equal to 0, the function was equal to 0 in place of y, then we would get x is minus 3 or x is 1. And these are the values where x squared plus 2x minus 3 equals 0 and the line y equals 0 are crossing. If we were asked instead to use this same graph, the same function, and solve it when it was equal to something else, like instead of just equal to 0, what if it was equal to 4x minus 3? We also talked previously that if we would take that then and say, okay, I can graph that line. I'll try to find the line where y is equal to 4x minus 3. Now you could make a table of values, or you could use your knowledge of gradients and y-intercepts to plot it, and you would plot a line that looks something like this. If I look then at where these two lines, one linear, one nonlinear, where do they cross each other? That's the solution to the simultaneous equations. There's one point that crosses up here and one down here. X is either 0 or x is 2. Now at those points, y is minus 3 or y is 5. So you have two pairs of solutions for this question. How do we do this without graphing? If we want to solve two simultaneous equations without graphing, well, we do it by substitution. As we've talked about, you could substitute in the place of the y, you substitute what was in place of y in the other equation. Then you rearrange it, and then you factorize it if possible, and that solves and gives you x equals 0, x equals 2, which are the same values that we just found by graphing it. Let's try another one. Here's another nonlinear equation and a linear one. Again, we could use substitution. We have one equation that says y is equal to 2x minus 2, so let's just put that in the place of y. Now watch carefully, you have to put it all in a bracket so that you don't lose the fact that the negative affects both terms. As you multiply through, it becomes minus 2x plus 2 in place of where that thing was put in as substituted in. Then you rearrange and make it equal to 0 on one side so that you can try to factorize it. This does factorize nicely, And it leads us to x is minus 1 or x is 3. If x is minus 1, then we can substitute back into our equation and find x is minus 1, y is minus 4. Or if x is 3, then y is 4, positive 4. So we have two values for x and two values for y. And in a nonlinear and a linear equation, often you do have two values. That means that the line and the curve cross at 2 points. Not always, but many times. We'll continue to talk about that throughout this chapter. Now, just as a little extra bonus, in your 2.1 section of exercises, you'll notice some equations which are actually equations of circles. So I just wanted to talk briefly about what is the equation of a circle, where does it come from, and how does this work in simultaneous equations. So the equation of a circle, it's not something I don't think we've formally talked about before, but it's not very complicated. Imagine that you have a quarter of a circle on a grid, and the center of the circle is the origin, 0, 0. If I would pick a point on the circumference of the circle, would I have enough information here on the screen to calculate the radius? What do you think? No, I wouldn't, right? I don't have any indication of scale. I don't know what that grid on x or y is equal to. So how can I know the radius? If, however, I wanted to find the radius, what information would we need? We would need to know the coordinate pair of that point. If I knew that pair, what is that x and y that it goes to, then I would be able to solve by using Pythagoras' theorem, because x1 squared plus y1 squared would be equal to r squared, and then I could find the radius. Does that make sense? I hope so. If I had another point on the circle, would it also work? Could we do this with any pair on the circle? Well, actually, yes, we could, because again, I can use Pythagoras' theorem, and that works regardless of which side, as long as I create a right angle triangle, and the radius is the hypotenuse. So this second point, if I had the x value and I squared that and the y value and I squared that, I would again get the radius squared. If you extend the circle now and show all 4 quarters of the circle, and the center is still at the origin, think about points all the way around. So if we know that Pythagoras' theorem lets us find the radius in that first quadrant, if we know any pair of coordinates, the question is, could we use a pair from any quadrant to find the radius? Or how will the negative values affect the calculation? Pause the video and just have a chat about it for a bit. What do you think? Can we? Yeah. All right, welcome back. Hopefully you chatted about it a little bit. We can actually use Pythagoras' theorem in any quadrant of a circle like this, because why? Why does it always work? Well, it works because I square any negative value and it will become positive. So it won't affect the length of the radius. If I have a negative x, I'll still just get what that x value is squared. And if I have a negative y, I'll still get y squared. So we can use Pythagoras' theorem from a coordinate pair in any quadrant to find the radius. This means that any x squared plus y squared is equal to the radius squared. And this is the general form of a circle when the center is at the origin. Because this equation links every point on the circumference to the radius, it is the general form of an equation of a circle with the center at 0, 0. All right, think you can remember that? All right, which one of these is the general form for the equation of a circle centered at the origin? Okay, pause the video and see if you pick A, B, or C. Okay, hopefully you didn't pick A and you did pick C. It is Pythagoras' theorem that links it. So we need to have x squared plus y squared. Now, why doesn't B work? What's wrong with B? Well, a diameter is not equal to a radius squared. Remember that. It's 2 times the radius. It's not the radius squared. So if we have this general form of a circle, this helps us to graph any circle that is centered at the origin. If I had something like x squared plus y squared equals 25, the easiest place to start is just to think, okay, so what if x was 0? Then, or what if y was 0? If x was 0, then y squared would be 25, so y must be positive or negative the root of 25, or positive or negative 5. And that's these points. Opposite way, if y was 0, then x would be positive or negative 5. So now if I want to draw a circle, and I know the center, and I know these points, I can just draw a circle. So you might notice that we didn't even need a table of values, or not many. If we know the intercepts, the y-intercept, the x-intercept, then we can know the radius and we can graph the circle. Remember, it's always going to be center at the origin in this form. So now you should be able to draw the graph of any circle, especially those that work out evenly. If it isn't a perfect square, it's not so easy to draw. But in this case, what was the radius? It was 5. And this was known from the equation. We just took r squared must be 25, so r must be 5. And therefore, we drew a circle. All right, here's one student for you to look at his work. Lucas has plotted this graph. X squared plus y squared equals 4. And here's what he says. I recognize this one immediately. It's the equation of a circle. And the graph took me only 30 seconds to draw. Okay, look at Lucas's graph and give me any coordinate pair to show why is Lucas not quite right? What did he do wrong and how should he have drawn his graph? Okay, pause the video and talk about that. Maybe share with a partner. What do you think? What did Lucas do here? Okay, hopefully you've had a chance to talk about it. If not, pause the video until you do. All right, let's look at Lucas's work. What did he do wrong? Well, if you take any coordinate point, like 0, 4, and you try to put that into the equation, you can see that 4 squared doesn't equal 4. What should he have done was take the root of 4, which means 2, and therefore the radius must be 2 for this circle. All right, so let's go back again to our main point was, what do we do algebraically if we have simultaneous equations with one linear, one nonlinear? So again, if this is a circle, we're just looking for points of intersection. So you can solve simultaneous equations even if you see x squared and y squared, and you follow the same basic principles. If you had these two, one circle and one line here, you could again use substitution. You could rearrange equation 2 to either have y or x on their own, and then you can substitute that into equation 1. Easier to do that than to be substituting with a square root if you try to isolate 1 from the first equation. You're going to have to multiply out this quadratic, expand x plus 7 times x plus 7. Don't miss that middle term. Then you're going to rearrange. If there is a common factor, you want to divide out that common factor. Here it's been divided by 2 to simplify it, and then factorized. And we end up getting x is equal to minus 3, in which case y would be 4, or x is equal to minus 4, in which case y would be 3. So we end up with this pair of solutions. This is the equation of a circle, we said, and this is a linear equation. So it might be curious just to know, what would that look like if you graphed it? It would look like a circle, and it would look like a straight line. And the straight line is touching the circle at 2 points. Okay? And those are the 2 points. It looks very close to being a tangent, but it's not a tangent. It actually crosses the circle at 2 points. So the solutions are the coordinate pairs of the intersections of the 2 lines, or the line and the circle. Okay, so if we have this pair of simultaneous equations, x squared plus y squared equals 100, x plus 2y equals 20, we could solve this either by drawing the graphs or doing it algebraically. Let's think about drawing the graph. If you were drawing the graph, you would first, for this circle, put in 0 for one of the x or y and find out what is that radius. We would find that y would be either positive or negative 10, and if you did it the opposite way, x would be positive or negative 10. It allows me to draw that circle. If I graphed this line, I could find points by putting 0 in for x. That would be y is 10. Oh, I already have that point. That must be a point of intersection. And then I could put in, when y is 0, x is equal to 20, and then I would have enough points to make a line, and I can see where they overlap. Here's the solutions. They overlap at 0, 10, and it's a little hard to read, but they overlap at 8, 6 on this graph. And that would be my second pair of solutions. Now, again, if I wanted to do this algebraically and not by graphing it, will I get these same 2 solutions? Well, hopefully, let's try it and see. If I wanted to solve this algebraically, then I would like to use substitution, right? So I would substitute x is equal to minus 2y plus 20. That's just by rearranging. And then I can substitute that into my first equation. Again, to do it algebraically, I have to do some expansion and not lose my negatives. And then I need to simplify it and pull the things together. At this stage, you would end up thinking, okay, maybe I should divide out. I have common factors here. Let's divide everything by 5 to simplify it further, and then I can bring the 20 over the left-hand side, simplifying it down to a quadratic that I can then factorize. I get y minus 6, y minus 10 equals 0. So y is either 6 or 10, which if you look back at the graph and those points, that's the same points we found by graphing it. So algebraically or graphing it, you come up with the same thing. Exercise 2.1 that you'll be working on doesn't ask you to graph things, it asks you to solve them algebraically. So that's what you need to know how to do. But keep in mind that you would get the same 2 solutions. So let's just wrap up here. What is the general form for the equation of a circle? It's x squared plus y squared equals r squared. And if you have this equation, you can know the radius and Circles and lines can be graphed to solve pairs of simultaneous equations, or they could be solved algebraically. And other nonlinear graphs and a linear graph, you can either solve them algebraically or you could solve them by graphing. And that's it for this lesson. You can do some exercises from 2.1 and we'll see you again soon. Take care.